the law of radioactive decay. The law of radioactive decay states that the rate of decay of radioactive element per second is proportional to the quantity of the material or elements that remain in a given time. Decay constant, the decay constant of a radioactive element is the instantaneous rate of decay per unit atom. Now, that instantaneous rate of decay per unit atom of the radioactive element is denoted as the number of disintegration per unit time. That is, it is proportional to the number of atoms present. So at this point, to remove this proportionality sign, I will introduce a constant. I will introduce a constant, and that constant is decay constant, which is lambda. So here, this is the decay constant. So if I introduce the decay constant, that gives the n over the t is proportional, is equals to minus lambda t. Call this equation 1. It is possible for us to rearrange this. If we rearrange this such that the n and n will be together using the variable separable method in calculus, then you have the n over n equals to minus lambda dt. Watch out, an error here. That should be n. So integrate both sides now. If we integrate both sides, you are going to have integral as you move from n naught, initial count rate or initial number of atoms, to n of the n over n equals to integral again as you go from 0, initial time t of minus lambda dt. So let's go to the next page. So at this point we have integral of n naught to n of 1 over n, the n equals to integral, bring out the negative lambda integral from 0 to t of dt. So at this point we are integrating with the lower limit n naught and the upper limit n, or with respect to n, and on this other part we are integrating with respect to t as you go from 0 to t. So integral of 1 over n gives you ln n, but the boundary still remains from n naught, the lower boundary, to the upper boundary n, equals to minus lambda. If you integrate the t, that gives us t as you go from 0 to t. Now the lower limit here, which is that of 0, is 0. That means it's out of this equation. So ln this n takes the value of the n here, then you have determinant sign between them which represent negative sign. Then we have ln n naught equals to negative lambda, as t takes the value of t, and if t takes the value of 0 again, you are going to have minus lambda, then t becomes times 0, which will be out. So we are left with ln n minus ln n naught equals to minus lambda t. Now if you see logarithm here, this logarithm now, for instance, if you have log a base b minus log c base b, this is equals to log a over c, which is still base b. So for this now we are going to engage with division. So that will give me ln n over n naught equals to minus lambda t. So once we get to this point, all I need to do now is to take the natural log of both sides. Take the natural log of both sides. Then we have take the natural log of both sides. So that will give me log e, natural logarithm of n over n naught equals to, take the natural log here, also log of e of minus lambda t. Now what we have here at this point is that the logarithm cancel the log, then we are left with e of n to n naught equals to minus lambda t. Now note, what we have here is something of this nature, e raised to the power of n over n naught, which is equals to minus lambda t. So therefore, if you rewrite this in logarithm form, it gives n over n naught equals to e, then this minus lambda t, the decay constant, will be taken as power. Then therefore cross multiply at this point to make n the subject of formula. You have n equals to this, we multiply e, n naught e minus lambda t. Now take this as one of the equation, the law of radioactive decay, but this time is known as the half-life, which is the time taken for the radioactive element to decay, and this is the number of atoms present in that element. So if we look for the half of it based on the fact that we have turned this t to half-life, then that means n, which is the capital N, the capital N becomes n naught over 2. So fix this back into this equation. So that equation becomes, and the equation is n equals n naught e minus lambda t. So that gives n naught over 2 as n turned to n naught equals to n naught e minus lambda, then the t here, the small t, becomes the big T, which is the half-life. So n naught, cancel n naught here, we are left with 1 over 2 on this side equals to e raised to the power of minus lambda with what? T. Similarly, if I take the natural log of both sides, I will have log e of 1 over 2, the left hand side, equals to log e of e raised to the power minus lambda with capital letter T. Then on this side, this is division of logarithm, it will turn to subtraction, log base e of 1 minus log base e of 2 equals to, according to power law in logarithms, minus lambda t comes behind the logarithm, that gives minus lambda with t logarithm of e to base e. Now logarithm of e to base e is like you have logarithm of a number to the same base, and the logarithm of a number to the same base is 1. Note log e to base e is taken as 0. Logarithm of a number to the same base 0. Similarly, logarithm of 1 to any base is 0. Note logarithm of a number to the same base is 1, which is 1. Then logarithm of 1 to any base 0. So if we fix that back into this above, log 1 to base e here becomes 0, so you have 0 minus log 2 to base e, then equals to what? Minus lambda with t. So you'll be left with minus log 2 to base e equals minus lambda with t. Negative sign cancel negative sign. Then you have log 2 to base e. Logarithm of 2 to base e is what you are left with. So we can just take that as ln 2. That is natural logarithm, which is ln equals to lambda t. Then make t the subject of formula, which is the half-life. T now equals to ln 2 over lambda. Now note, ln 2 is same thing as 0.693. So therefore half-life t is 0.693 over wavelength. That is half-life. If you cross multiply now, that means the K constant also is 0.693 over half-life, and that is a proof of the equation of the K constant.